So it's my pleasure to talk and to be here to talk about this project. So today I would like to explain to you something that we work about with my colleague from University of Orléans, Aurélien Alvarez. I don't know, he's here. George, I don't know if you know the photo, and you know the guy. You know, you wrote some of his text, but so we work on plane algebraic foliation in the complex domain, and the goal of my talk is to describe some stability component, namely some algebraic foliation of the complex projective plane in degree 2 that is structurally stable. This is kind of the goal of the talk, and what I would like to begin with is to report on the history of that problem that begins in the 50s in Moscow. Is it okay? So Landis, Evgeny Landis was in Moscow in the 50s. He had two students, very smart students. First one, Uday Verenov, he proved the following statement, the following theorem, which is that you may, so you consider some differential equations of this form in the complex plane. So U and V are complex numbers. P and Q are complex polynomials of degree D. And you look at this differential equation with the complex times also. And he proved that if P and Q are chosen generically in the set of couples of polynomials of degree D, then all the integral curves of such a differential equation are dense in the complex plane, apart from a finite set of points corresponding to the equilibrium position of this differential equation. So there are a finite number of points where P and Q vanishes simultaneously, and those points, the solutions are constant. But apart from these special equilibrium solutions, the trajectories of this differential equation are dense in the complex plane. So it was a kind of surprise because, of course, we all know the theory, Poincaré-Bendixson theory. If you replace, I mean, if you consider the real such real equations, we know that the solutions are going to accumulate on some cycles or equilibrium position, and that was a theorem proved by Poincaré and Bendixson at the beginning of the 20th century. And so in the complex plane, in the complex situation, it's very, very different. And there was some complements of that theorem that was achieved by Ilyashenko some years later. So he considered the same setting. So we have exactly the same kind of differential equation, polynomial differential equation in the complex plane. And what he proves is that, so we know that generically leaves are dense, so the equation is called minimal, but he also proved that it is ergodic, namely that you cannot find a first integral which is measurable, apart from almost surely constant function. So first integral it's a function of the variable u and v, which is constant on the solutions of the differential equation. So it is not possible. Another way to say that it is not possible to have a partition of the phase space, so the uv bar variables, into two measurable subspace that are union of solutions of the differential equation. So it is ergodic. So this is a theorem of 68. And 10 years later, he proved that it is also locally rigid, namely that if P and Q are generic, so essentially it says that if P and Q are generic, you cannot find a topological conjugacy between such a differential equation and another one. And in fact, you can, but if you can, this means that the two differential equations are conjugated by an affine transformation of the complex plane. So you have this kind of rigidity statement that was proved in 78. That was yes. So what he proved that is that in fact it's not exactly true what I said. So the precise statement is that you take a generic equation like that, and you take another one which is sufficiently close to that one, and you assume that there exists a topological conjugacy between the two that is sufficiently close to the identity. Then, in fact, you can find such a conjugacy which is an affine transformation of C2. And right, so that was the two theorems that was proved by these two. That was proved around the 60s, and the tools to prove these statements is to study the holonomy at infinity. So let me just say a few words about that. So if you take P and Q generic, degree D polynomials, it turns out that if you consider the foliation induced by this differential equation, so it's the foliation of the complex plane, and it can be compactified as a holomorphic foliation of the complex projective plane, and the line at infinity is going to be invariant, and it's going to contain d plus 1 singular points. So the line at infinity is going to be a leaf of a foliation apart from this finite set of points. You will have some separatrices, other separatrices for this foliation, and so the foliation around the line at infinity is going to look like this. So the leaves are like this. But of course, this line at infinity is a complex line, so it's a sphere minus a finite number of points. And when you have a leaf of a foliation, you can consider the Monomi representation, which is defined the following way. If you take a path, a loop, say, in the line at infinity that turns around a singularity, you might look at the first written map. I mean, you can look at the solution close, starting close to that point, and try to follow that loop. When it returns back to that transversal, you might have a different point, and that defines a germ of diffeomorphism of that transversal to itself that fixes that point. So if you take a parameter, a coordinate on that transversal, you get an element, a germ of diffeomorphism of the complex numbers that fixes 0. Right. And so you get a representation, holonomy representation, from fundamental group of the line at infinity minus the singularities of the foliation to this group of germs of diffeomorphism of the complex line that fixes the origin. And in fact, the two theorems that I described eventually can be proven by this kind of statement, namely that if you take a generic subgroup of germs of diffeomorphism fixing the origin in the complex numbers, then in fact it is minimal at the neighborhood of the origin. So namely the orbits of that group close to the origin are going to be dense on some neighborhood of the origin. It is ergodic also, and it has a rigidity property. So namely, in fact, you have just to have such conclusions, you just have to assume that the multipliers of the element of your group at the origin forms a dense subgroup of C star. And so this kind of statement was proved by Uday-Verenov and Ilyashenko. And there was complement of those works by Sherbakov, a student of Ilyashenko, and Nakai, who gave the right conditions, I mean the precise condition on a subgroup of germs of diffeomorphism of the origin so that such conclusions are valid. I will not describe these complements now. This is not really the subject of my talk, but just I wanted to say how we can prove such statements. The problem to deal with when we study foliations of the complex projective planes, say, which is the subject of my talk, is that in general a foliation of the complex projective plane does not preserve any line or any algebraic curves, in fact, generic foliation. And so we cannot apply this kind of techniques because really the techniques here relies on the existence of a group. And so if we want to deal with foliations of the complex plane, we really need to adapt this technique to pseudogroups. And this was the goal, and they achieved to do that. Franck Lorraine, Jules Rebello, in beginning of the, say, 2000s or something. So they proved that we have the same kind of results in the moduli space of foliation without any condition of preserving some algebraic curves. So namely, they proved that there exists, if you pick a degree, at least 2, there exists a non-empty open subset in the moduli space of degree D algebraic foliation of the complex projective plane, consisting of foliation that are minimal, so namely all the leaves are dense apart the singular points, ergodic, the same definition, and locally rigid with the same definition. And the technique is to try to adapt, I mean, this lemma just before for the groups of germs of diffeomorphisms fixing the origin to pseudo groups. In fact, these techniques were initiated by Gis in the 90s and are based on the nonlinear versions of the Zassenhaus lemma, for those that knows this lemma in the context of subgroups of Lie groups, so of linear groups. But okay, so the goal of my talk is to present some other foliation, other parts of in the moduli space of foliation where all these phenomena are completely are not valid at all. So this is the goal of the following results. So what we proved with Aurélien is that if you take so the first part of our theorem is that if you take that foliation, so you consider this differential equation in C3, this is a homogeneous differential equation of degree 2. And so the foliation induced by that foliation, that differential equation in C3 is invariant by multiplication by the scalars. So it descends to a foliation of complex projective plane, which is called the Jouanolou foliation. In fact, it was introduced by Jouanolou in the 70s to prove that a generic differential equation of P2 does not have any algebraic curves. That does not have any algebraic leaves. So all the solutions, all the leaves of this foliation are transcendental curves. And so what we proved is that this foliation is structurally stable, namely that if you take a foliation which is sufficiently close to it, you will be able to find a homeomorphism that of P2 that sends the solutions of G2 of the Jouanolou foliation to the solution of the perturbation. Right. So all the foliation close to P2 have the same, so close to the Jouanolou foliation have the same phase space up to a homeomorphism. So of course, it can be opposed to the rigidity properties in the theorem of Ilyashenko. And we also have that for this foliation, we also have this property that we can find a Fatou component. In fact, as in, there was a definition of a Fatou component for a holomorphic foliation that was originally given by Gis, Gomez-Mont, and Saludes, which is essentially the set of points where the holonomic pseudogroup form a normal family, has exactly the same definition as in the context of iteration. And in fact, we can prove that that Jouanolou foliation, its Fatou component is non-trivial. And in fact, it is it has on that, so this is an open set, which is saturated by the foliation. Namely, this is a union of solutions, a union of leaves. And on this set, we have a first integral, which is holomorphic, with values in a genus 3 curves, which is a Klein quartic. So this is this this quartic equation in the plane. And the leaves in this domain are disks. So in fact, it is a C infinity fibration of disk onto this Klein quartic. So we have this. It's not at all holomorphic. It's exactly the same kind of thing that has, like Lefschetz vibration or things like that. This is infinity. Locally, this is a trivial. This is locally a product in the infinity category, but not in the holomorphic category.
But still a holomorphic vibration. You have a map to the Klein quartic.
You have a map which is submersion, and this map is a C-infinity vibration, but it's not locally holomorphically a product.
Yeah, vibration is not holomorphic.
No, exactly. So this is exactly. Yes, but how do you call, so I'm sorry, so maybe, so what is a holomorphic vibration? There is a, you can say, you could imagine that is locally holomorphically trivial.
Oh, no.
So how do you call this kind of object? Isotrivial vibration. Okay, so if so, I agree with you. You can call that holomorphic vibration. It's not isotrivial. Right. So here I draw the famous tilings of the hyperbolic plane, which define a group, a discrete subgroup of the isometries of the hyperbolic plane that defines the uniformization of that Klein quartic, famous tiling that was discovered by Klein. Actually, it is a picture that you can find in the Klein book. So as you see, so of course, leaves of that foliation, Jouanolou foliation, are not dense because leaves containing that domain cannot be dense, and leaves on the complement of that domain, that Fatou component, are not dense neither. And also this foliation is not ergodic at all because you have this first integral on some non-empty open set. So it's not ergodic. So this is really so you really have two open components, disjoint open components in the moduli space of foliation where you find really distinct dynamical behavior. If I have time, I will show you some pictures that are not in this context. We are not able to produce some pictures. It's kind of challenging problem. But I will show you some other kind of picture in other parameter family of foliations. Let me just say a few words about this problem that was asked by Anosov in the 60s or 70s. So this is the following question, that if you take a foliation of degree D, which is generic, so the leaves of that foliation should be simply connected apart from a countable number of them that are annuli, topological annuli. And so this conjecture is not, of course, D is equal to 1, it's really easy to prove, but beginning from D is equal to 2, it's quite open. And the techniques of the proof that I am going to describe later permits us to verify that conjecture for the Jouanolou foliation, in particular for an open set of foliation, because this is a property which is, of course, invariant by conjugation. So maybe I will have I will tell you a few words about these and from where the annuli are coming. For the Jouanolou foliation, we can understand very well these annuli, and this is, there are plenty of questions that we can ask about this, but I think this is interesting to have this partial answer to that conjecture in degree 2. Okay, so I'm going to try to explain to you the tools that we developed and kind of the idea of the proofs, some ideas of the proof. So beginning from now, I will just forget a minute the Jouanolou foliation, and I will start with the degree D foliation, algebraic foliation of the projective plane. And I would like to explain the criterion which is going to ensure structural stability and the existence of these Fatou components. So the first thing that you have to know about foliations of the complex projective plane is that they are all given by projectivization of a certain homogeneous vector fields on C3. And so exactly as the Jouanolou foliation that we just saw a few minutes before. And in fact, you have various possibilities. So if you add to a homogeneous vector field a multiple of the radial vector field in C3, you get exactly the same foliation. And in fact, you can normalize. You can, if you add such a multiple of the radial vector field, you can always assume that the divergence of the vector fields vanishes identically. If you do that, this homogeneous vector field is almost unique up to multiplication by a constant. So in fact, the moduli space of degree D algebraic foliation is a Zariski open set in the projectivization of the divergence 0 homogeneous vector fields of degree D. You can see describe this moduli space like that. And just observe that the Jouanolou foliation, which is just that one, in degree D, so this, say, call this homogeneous vector field JD. This it is a representative with 0 divergence. Okay, so we take these vector fields, and now the main new tool in our study of that foliation is to introduce this gradient vector field. So this is a vector field on P2, which is going to be not at all holomorphic. It's a real vector field, which is tangent to the foliation, and which is going to have some nice hyperbolic properties. So let me just describe. This is completely general. For any foliation, you can do that. So you take this function, which is just a log of the Hermitian norm in C3. And in fact, you can play with other kind of functions, but this is the most simple one. And then you consider the gradient of that function along the solutions of your of the homogeneous vector fields in C3. So in C3 you have some these integral curves that are Riemann surfaces immersed in C3, and you can, along these Riemann surfaces, you can take the gradient of that function, right? And this defines real vector field on C3, which is tangent to the foliation induced by the vector fields V. And in fact, if you take the gradient with respect to a nice Hermitian metric, then you will get that these vector fields on C3 is invariant by multiplication by the scalars. And so it descends to a vector field on P2, which is going to be tangent to the foliation. So that vector field is called the gradient vector field. And these gradient vector fields, in general, it has very nice hyperbolic properties, hyperbolicity properties, which are the following. So in fact, it expands. So in fact, the leaves are unstable, namely two solutions of the gradient vector field in the same leaf of the original holomorphic foliation diverges. So namely, the picture should be like that. If you have, apart from the singularities of the gradient vector fields, you will have the following pictures. So if you take two trajectories of W that lies in the same leaf so this surface is a leaf of the foliation. Two trajectories of W in that leaf are diverging. And transversally, along a W trajectory, transversally it is contracting. So you have a transverse contraction. And in fact, if you think a little bit, it's very easy to establish the first property. So that property is just the fact that the log of the norm, Hermitian norm, is a plurisubharmonic function. And so if you take the gradient of a plurisubharmonic function, you get this phenomena along a leaf. And the fact that you have the transverse contraction is a little bit more difficult to establish, but it relies on the fact that, in fact, if you have a holomorphic foliation, you have the Bode connection. So the Bode connection is a connection on the normal bundle of the foliation, which is defined only along the directions tangent to the foliation. And in fact, if you think a little bit, if you have a homogeneous vector field that defines a foliation on C3, you can think of that as being a connection along the foliation on the tautological bundle, right? And in fact, what we prove is that the condition that the divergence of V is equal to 0 is exactly saying that this Bode connection is given by that homogeneous vector field. It's a very easy calculation. And in fact, then you get, so then the transverse contraction is just the fact that we took the gradient along the solution. So. W is a gradient vector field. So W is a gradient vector field, by definition. Okay. So it just means that. So it just means that if you take. So this is the normal bundle to the W trajectories in the tangent bundle of the foliation. So it is a real light bundle of dimension 1. And on that bundle you have some dilatation. So you have this expansion. So infinitesimally it says that in the normal bundle, in that normal bundle you have expansion, right? Okay, so this is extremely general, and now, but of course, these hyperbolicity properties cannot just prove anything because we know that we have this Lorer-Rebello foliation that are minimal, etc. In fact, our criterion is the following. So you take same notation, same setting. So we have V, a homogeneous vector field of zero divergence. We consider this function log of Hermitian norms. If this function along trajectories are only local minimum, so if its critical points along the V trajectories are local minimum that are non-degenerate, in fact, we can prove that there exists a Fatou component exactly as I described. So this is a holomorphic fibration over connected compact curve of genus that formula. And if, moreover, we assume that the singularities of the foliation are hyperbolic, namely that the quotient of the eigenvalues at each singular point of the foliation are non-real, then we also have the structural stability of the foliation. In fact, it turns out, in terms of the gradient vector fields, this assumption, so the main assumption here is about the critical points of that function along the V trajectories. This is really the main assumption. And let me just say what it means in terms of the singularities of the gradient vector field. So the gradient vector field has two types of singularities. So of course, so by singularities I mean the zeros of that vector field. You have the singularities of the foliation itself, but you also have singularities in the regular part of the foliation. These singularities correspond to the critical points of F. So this is exactly along the V trajectories. This is exactly the singularities of the gradient of a function are located where the function has the critical point, right? So what I want to say is that I am going to call B, this is a set of singularities of W in the regular part of F. And in fact, assuming that the critical points of F along the trajectories are local minimum is the same as assuming that the singularities of W along in the regular part of F looks like that. So you have a source as a singularity along each leaf, right? A priori, in general, so for instance, in the context of Lorer-Rebello, you will see some singularities that are saddles. But in our assumption, we assume in our criterion says that we do not see these kind of singularities. Right? We only have these kind of singularities. And so the proof, so let me just say the idea of the proof of, say, the structural stability. So if you have such an hypothesis, of course, if you consider those singularities, they are going to be organized as a real surface which is transverse to the foliation. So this B, under our assumption, this B is going to be a transverse a surface which is transverse to the foliation. And in fact, if you take a certain tubular neighborhood, if you take out a certain tubular neighborhood of B, you get a four-manifold with boundary, and the gradient vector field is just transverse to that that boundary. And also, you can play the same game at the singularities of foliation, but there is a kind of trick to make that gradient vector field transverse to some sphere around the singularities that I'm going to skip now. But so at the end, you get a 4-manifold with boundary, and together with a vector field which is transverse to the boundary. And this vector field is hyperbolic, as I explained. Now we have taken out any singularities of that vector field. It is a hyperbolic vector field, and we can apply we know that it is going to be structurally stable by the theory of classical dynamical system for flows. And in fact, this is exact. So this property will be very helpful. So I just tell you the ideas. So then those are kind of technical details. But the idea is the following. So we know, first of all, we know that it is hyperbolic, and we know that the weak unstable leaves of W by this picture are exactly the leaves of the original foliation F. Okay, because we have transversally we have contraction, and the expansion are only given in the direction of the leaves of F. Right? So we have that the weak unstable leaves of W are leaves of F. So what is going to happen? If you take a small perturbation of F, say F prime, you will be able to deform W in a real vector fields W prime, which is going to be tangent to that foliation F prime. It's really easy to do that. But that W prime is going to be a perturbation of W. Because W is structurally stable, that W prime is going to be topologically conjugated to W. And the topological conjugacy are going to send the weak unstable leaves of W to the weak unstable leaves of W prime. So it's going to conjugate the foliation F to the foliation F prime. And we get the result. So of course, so this is very easy. And it's a little bit more complicated than what I said, because in fact, what I said is going to work very well in the Julia set, so in the complementary region of the Fatou set. But on the Fatou set, we have to do some different argumentation. But essentially, the idea is there. Let me just say a few words about where comes these Fatou components. So these Fatou components come from there. So here, if we have such a situation, you can observe that if you take, so suppose B, I take a point B in a singularity of W, which is not a singularity in the regular part of the foliation F. So by assumption, we know that it is a source. It is like that. Now, the trajectories of W that originate from that point. So there is a circle of trajectories that originate from that point, and they can never go back to that surface B, right? Because at another point of B, we have the same picture, and this is a source, so you cannot come back to B. So in fact, this B is a kind of expansor for the W, and so you can prove that all these W trajectories are all disjoint, and the idea is that their union is going to describe the whole leaf of the foliation F passing through the point B, right? So you see, you get a parametrization of that leaf by a disk. It's kind of extremely simple, but So we get that all the leaves passing through points of B are disks, topological disks. This is related to the Hanosov conjecture that I explained before. And in fact, you see also that the union of those leaves that never come back to B, right? This is a fibration by disk over B. So then, so this fibration by disk over B is exactly the Fatou set, the Fatou components that I described. So just let me just indicate for, I don't know how much time. Yeah. Let me tell you why we have this this topology for B. So how do you can compute, for instance, the Euler characteristic of B? So this is something which is kind of interesting in itself. Suppose so let me just tell you a small theory about surfaces that are transverse to a foliation of P2, real surfaces. Suppose F is a degree D algebraic foliation of P2. And suppose that B is a real surface in P2, which is transverse to F at every point. So it does not pass. It does not contain any singular points of the foliation, and at every point it is transverse to the tangent to the leaf passing through that point. So then, in fact, what we can prove is that B is going to be a union of torus, topology of B, of tori, say, and a kind of big component, which is a connected surface of genus. That formula, 1 plus. So let me just prove that. I'll try to prove that. No. So first remark is that if you have such a surface which is transverse to foliation, in fact that was so of course it inherits a complex structure, because we can restrict the transverse structure of the foliation to B to get a Riemann surface structure on B, right? So in particular it is an oriented surface. So B is oriented, of course, and it has a holomorphic structure, but of course this is not a holomorphic curve, right? It is a real surface. But it has a Riemann surface structure which arises from that situation. And so if it has an orientation, it has a degree. If we look at the fundamental class of B, so we can write, so because the second homology group of P2 is Z, we can write that B is some integer that I call degree of B times the fundamental class of a line, right? Okay, so let me just now prove that such a B has such a decomposition. For that, I can suppose that B is connected. And if B is connected, I have to prove that it is a torus or a connected surface of that genus. Let me just do that. So we can assume that B is connected. You will see why in a moment. So let's just begin by the fact that B is connected. Let us assume, say, better say like that. Now we are going to, let's assume, first assume that B is connected. Okay, so what is the self-intersection of B? So first of all, this is the square of its degree, right? Because the intersection form of P2 is what it is. And now it is just the intersection of fundamental class of B and the tangent, the chain class of the tangent bundle to the foliation. Right? We know that the tangent bundle to a foliation is O of 1 minus D. Right? So it gives 1 minus D times degree of B. So if the degree of B is different from 0, it means, by simplification, that in fact the degree of B is 1 minus D. It's kind of strange. We get something which of negative degree. Right? We really see that this is not at all holomorphic. Anyway, we know that holomorphic curves, we have many tangency points with the foliation. Right? So this is kind of. And so we have that formula. And now we can compute the Euler characteristic of B. So the Euler characteristic of B is just the intersection. It's just the chain class of its tangent bundle. The tangent bundle of B is just the restriction of the normal bundle of the foliation to B, right? Because it is transverse. So we get that formula. And we know that the normal bundle of a foliation is O of D plus 2 right. So we get that this is we get that formula. So you see that if the degree of B, so either the degree of B is 0, and then the Euler characteristic of B is 0, and that we have torus, or it is non-zero, and then the degree is 1 minus D, and we get that the Euler characteristic is just D 1 minus D times D plus 2, which gives you the formula. And so, if we have a disconnected surface, there might be one component with non-zero degree, but it is unique because if we have two, they should intersect in P2 because of the intersection forms in P2. So if B is disconnected, there must be only one component of non-zero degree. And so you get that statement. Okay, so this is where comes this computation of the topology of that of the quotient of the Fatou components. So this is exactly so. This is the first step because now we have to prove that there cannot in the quotient of the Fatou set there cannot exist tori, and this is another kind of arguments which demand some dynamical system argument. I will not go into that now. But so apart from that, we see from where comes these numbers. Okay, so just let me tell you. So we are able to prove that in degree 2 the Jouanolou foliation satisfies our criterion, and in fact. So it's not. So the good news of this criterion is that in fact to prove that this criterion is satisfied, we just have to verify that some inequalities, algebraic inequalities, are satisfied in on a real algebraic manifold. So in the case of Jouanolou foliation, so because to verify that the critical points of f along the v trajectories are a local minimum is just computing the index, and computing the index is just a matter of an inequality on the partial derivative of the function along the v trajectories. In fact, if you look at the Jouanolou foliation, the inequality that you have to satisfy is the following. So you need to satisfy this inequality in C3 on intersection to that manifold. This manifold is exactly the equation of the critical points of the function along the v trajectories. So this is the equation of B. is a B equation. B. So projectivization of that equation gives B. In fact, this is what is called a mixed curve, because it is defined by polynomial expression in the complex variables and anti-holomorphic variables. So, to satisfy our criterion, we need to prove that this inequality is satisfied on that B. And in fact, we don't have any good proof of that. So our proof is numerical. We use a computer. So we use some approximations. This is really a proof, but it is done by a computer. Namely, what we do is that we can approximate that B by integer solutions, that points that are sufficiently close to B, and using kind of in fact, if we are able to satisfy such an inequality on those points, which is a little bit better than that one, then we know that that inequality on the real points of B is also satisfied. And so at the end, we have, say, I think this is 10 million of points with integer coordinates. And we verify by a computer that such inequalities, kind of similar inequalities, are satisfied. And this is more or less what we do. So we know for sure that this will be true, but the proof is kind of dirty in a sense. So of course we have tried to use some Hölder inequalities, or I mean plenty of things, but we don't. So if you have an idea, it would be nice. It took us like 1 year to do that work. But anyway, so we know that for Jouanolou foliation is true, and experimentally we know that for Jouanolou foliation in any degree, it seems to be true also. We have some similar equations, and we can play with that, but we are not able to do that work. I mean, the computer-assisted proof is too complicated to do. But it seems to be true. So probably for any D, the Jouanolou foliations have the same kind of properties: structural stability, Fatou component, and blah blah blah. Okay, so let me just say a few words about So we proved that the Jouanolou foliation is structurally stable. So namely, close to that Jouanolou foliation, we see foliation having exactly the same phase space up to a homeomorphism. But we can look at the whole set of foliation having that shape, right? And it's going to a priori, it's not completely clear, but we can imagine that this set is going to define an open set in moduli space of foliations. And in fact, if you count parameters, you see that you have the same number for parameters of foliations of P2 of degree 2 up to action of linear groups. And actually, this is six complex parameters. And the number of parameters for moduli space of curves of genus 3. So the quotient, and I think that this is not a coincidence. The explanation is that for a foliation in the stability component, the structure of the quotient of the Fatou component, which is a curve of genus 3, as I explained, gives you encodes the whole structure of the foliation. So it makes exactly as the same as in the theory of Kleinen groups. We probably have a kind of dictionary between these stability components and the geometry of the foliation inside the stability component and Teichmüller geometry. But of course, it's highly conjectural. We do not know how to prove that, but it's really possible. In higher degree, that conjecture will be false because you have more curves of genus than moduli of foliations. So you have So the quotient of the phi 2 components has some hidden symmetries that we do not understand, but it's probably interesting to understand that. Okay. I think it remains me to some 5 minutes, so I'm going to describe other parameter families of foliation where we knew there was this dichotomy stability components and foliations that are unstable, ergodic, etc. So these foliations come from the study of linear differential equations on Riemann surfaces that can be written like that. So here, I just take linear differential equations on the Riemann sphere. This is already very interesting. And so if you take second linear differential equation, second order differential equation, you get you can associate to that a foliation in the TV plane, right? And so those are extreme. So in the TV plane, you will get a Riccati equation. And in fact, we know that the monodromies of these foliations are completely encoded by their monodromy, which are Kleinian groups in general, so groups of Möbius transformation of the V variables. And we know that sometimes these groups are going to be structurally stable as Möbius groups, and sometimes they are going to be unstable. And there are some pictures that have was produced by David Dumas. So here, this is a kind of slice in the PQ parameter space. This is one-dimensional slice. So in red, you see the components where you see stability. So it means that the monodromic group is a convex co-compact in PSL2. This is a convex co-compact subgroup of PSL2C. And in black, you see the instability regions. Okay. So I show these pictures because I would really like to show the same, to make the same picture in the context of moduli space of nonlinear foliation of P2, but at the moment we are not able to produce such pictures. But it's possible that we have plenty of components. So as you see here, we have plenty of components, of stability components that are attached to each other in a very complicated way. So it's very natural to conjecture that the same kind of phenomena are going to happen in complex foliation of degree 2. But of course, for now, we know just one stability component. And what I want to, yeah, so I've said everything. And this is all. So I said the conjecture. So just to finish, I mean, in the course of this work, we have some pictures for the Julia set of the foliations. It's just experimental pictures. And it seems that the Julia set has a combinatorial structure very close to the one of the Lorentz attractor, which is a flow in R3. So it has an attractor. This is given by that differential equation, very famous equation. It has an attractor which looks like that. And in fact, we see something very similar, apparently, for the Julia sets. But we don't know how to prove anything like that. But I hope we will be able to do that. Anyway, so I'm going to finish now. Thank you very much.